Welcome to Leetcode JavaScript, a channel where we solve every single Leetcode question using JavaScript. Today we have 2136 earliest possible day of full bloom. This is a hard question, but isn't that hard for being a hard question. So let's begin. You have n flower seeds. Each seed must be planted first before it can begin to grow. Then bloom. Planting a seed takes time, and so does the growth of the seed. You're given a zero index array's plant time and grow time. Each plant time I is the number of full days it takes to plant the ith seed. Every day you can work on planting exactly one seed. You do not have to work on planting the same seed on consecutive days, but the planting of the seed is not complete until you have worked plant I days and planted in total. And growth time I is the number of full days it takes the ith seed to grow after being completely planted. Up to the last day of its growth, the flower blooms and stays bloomed forever. From the beginning of day 0, you can plant the seeds in any order, and we want to return the earliest possible day where all the seeds are blooming. This might not be the easiest thing to understand, however, it really isn't that complicated. So you're just given an amount of time that you need to plant each, and then subsequently you can correlate that to the time whenever it's gonna bloom, right? So there's a couple ways to solve this, and the better way to do this is sorting everything related to growth time, such that we make sure to plant whatever takes the longest to grow first, and then that way we minimize the time altogether. Now we're gonna have to do some sorting, so this algorithm time complexity is gonna be O of n log n, and this is also a bit of a greedy algorithm. And if you know anything about greedy algorithms, is that they're kind of very ad hoc or very specific to a situation, so there's not a good chance you may be able to apply this particular algorithm elsewhere. But it's still good to know. So we're gonna map the plant grow and plant time such that we can sort things. Now, the easiest way to do this is using an array. We can use a hash map, no problem, but I'm just gonna create an array, create times. Now, we're gonna do a simple for loop. It's equal to plant time that length and I++. Okay, so far so good. Now times I, or rather times that push, and we're gonna push every single time. We could push rather a map or object, or we could also, since we don't have a one-to-one correlation, we can just have an array instead. And we're gonna have plant time I, comma, grow time I. So in this case, we're simply gonna push the couple or the pair that corresponds to each other. For example, in the first example, we have 1 and 2, and that's gonna be pushed first, and secondly, we're gonna have 4 and 3, and finally 3 and 1, just that we have the corresponding values as needed, and then we're gonna sort them. Okay, afterwards, we're gonna do times that sort, and we're gonna use the following comparator for that, and that's gonna be b1 minus a1. So what are we doing here? We are using the sort function of JavaScript to sort this in descending order related to growth time. Let's look at an example. So in the first example, we have 2, 3, and y, and 1 as growth times. In this case, we end up with an array that can be represented as 3, 2, and 1, meaning the plant that takes the longest amount to grow goes first, and it descends from there. And since we have mapped that to the plant time, we can take that into consideration later to do the calculation. Now, we need a total variable that we're going to initialize as 0 initially. That's going to be total plant time. And we also are going to need a total time in general. And we're going to have to loop through. Yeah, okay, I forgot to initialize this variable. And we're going to have to loop through plant time again. Time dot length. We have I++. Okay. So here we're going to add to total plant the times I 0, meaning for each element of times to the total plant time, we're going to add the first number, which in this case is going to be the plant time. So after being sorted, the plant time is going to look something like 4, 3, and 1. So in the first example, we're just going to add 4. Alright, now the total time is going to be equal to math then max of the current total time and total plant time plus times I1. And finally, we're going to return total time. Let's run this code. And it is accepted. Now let's go through it once more time, because this might not be the clearest thing. Because again, being a greedy algorithm can be very situational, so it might not be super obvious what we're doing. So from the top, we're creating a times array, and this times array is going to map every plant time to every grow time, so we can sort it later. And how do we sort it? We decide that we want to plant whatever takes the longest to grow first. And that's the greedy part. We assume that it's going to give us our correct answer. And in a problem of this nature, that's almost always the case. And in this problem in particular, it is the case. So we don't have to worry a whole lot about it. We simply use this comparator to do so. Then we keep track of the total plant time for a given seed and the total time altogether. And we compare the current total time, that of course is first is initialized at 0. And we compare with the total time plus the time to grow. And finally, we return the total time that is guaranteed to be the minimum, or rather the earliest, day of full blossom. Now let's submit this code. And it was accepted. Again, the time complexity of this is, I'm gonna write it down here, is O of n log n. Why is that? We can see that we have for loops through plant time. So that's going to be O of n, where n is the length of plant time. However, times needs to be sorted, and the length of time is n. And the fastest you can sort an array is O of n log n. And the space complexity is O of n, because the auxiliary space that we use times that has the same length as plant time. Thank you very much for watching. Don't forget to like and subscribe.